Okay, so let's proceed. It's been quite a while now, but try and remember what we talked about at the end of the last lecture was the so-called Boltzmann equation. So the idea was that we wanted eventually to find an equation that could tell us how particles interact and whether they are in equilibrium or out of equilibrium, and how to describe that whole decoupling process or recoupling or whatever it is, particles drifting in and out of equilibrium. Right, so the thing is that the tools we're using is what you would call classical statistical physics, meaning that the fundamental quantity that we're always working with in this game is called F. So that's the one particle distribution function. So that particular function tells us how many particles are there in a certain location in six-dimensional phase space, meaning the space spanned by normal coordinates and momentum, so the canonical coordinates of analytic mechanics. Of course, now we are throwing out anything, for example, related to entanglement, to memory in quantum systems, and so on. So we are basically talking about gases of free particles which can interact, but where the interaction is described as something that occurs in some sense infinitely fast relative to the time span between collisions. And that is a very good approximation, as it turns out. I don't think we will go into much detail in this course, but that's a very good approximation if you talk about cosmology, because cosmology is, always physics in an extremely dilute medium. It would be a very bad approximation, for example, if we looked into the interior of a neutron star, say, and we wanted to talk about particle interactions. We certainly could not use this formalism. But here, at least in late time, cosmology is a very good approximation. So the equation that we're after is some kind of equation for this one particle distribution function. And whatever the equation is, it must be some form of conservation equation that contains, for example, all the classical normal conservation laws like energy and momentum conservation. So what turns out to be the case is that this conservation equation for the distribution function can be cast in the following super simple way. So it basically says that distribution function is conserved if you do the derivative in the way that is in fluid mechanics called the material derivative. So you do the derivative along motion of this fluid or this phase space element. So that is what these derivatives are taken to mean. And of course, by applying the chain rule, we can convert these into normal coordinate derivatives. So by the chain rule, we could write this conservation law in the following way. Like this. And here we have, for example, velocity and spatial gradient of the distribution function. So it basically just tells you very simplistically, if you have if you have a blob of matter in phase space that sits at a certain location in space, then if it has velocity, it moves to another location. That would deplete the amount of phase space material that you have in this one particular coordinate location. Of course, if you just do the derivative along the lines of the motion, you wouldn't see this because it would be a conserved quantity. Same thing, this is a force term. If you apply a conservative force to the system, then you move particles and therefore phase space matter around. And these coordinate derivatives are certainly non-zero in the general case, even though this material derivative is equal to 0. Now, in general, it's not true that the right-hand side is 0. It's only true if you have some kind of matter described by this one-particle distribution function that is only acted upon by conservative forces. So that means anything to do with, for example, production and annihilation of particles cannot be taken into account in this equation. If you have two species that can exchange energy or momentum, that cannot be taken into account in this way, because we're assuming that momentum and energy, for example, are explicitly and exactly conserved within that species. So this applies only in what is known as the non-interacting limit, or the case where particles have no interactions at all, except for, in this case, gravity, because that's the only conservative force that we're interested in. Okay, so we'll get to cases where the right-hand side is different from 0 in just a little while. But for now, we're just looking at the non-interacting limit. Now, in a homogeneous and isotropic universe, most of these terms are actually 0 explicitly by symmetry. So, for example, something like a spatial gradient certainly must be 0, right? It's also true that some of these momentum terms are 0. So remember what we did last time. We split this into a magnitude of momentum like this, and a direction of momentum. So we have a p hat vector here, like this. And clearly, the distribution function should not depend on the direction of momentum, because that would violate the cosmological principle. So that cannot be there. On the other hand, all normal distribution functions for particles would typically depend on momentum. They must depend on momentum. And that means this term must be non-zero, essentially in all cases that we can think of. And therefore, we're left with a total of just two terms in this Boltzmann equation, namely the explicit time derivative and then this term here. Now this term we can rewrite slightly. We can actually find the momentum derivative here, the time derivative of the momentum. And the way we do it is to use the geodesic equation. Because remember, we know that the magnitude of momentum scales as a to the minus first, right? It drops as the universe expands and the scale factor grows, momentum drops. And therefore we could write this as this differential equation, which we then integrate to get this. And we could, of course, now do this as a time derivative like this. And now we're almost there, because this is just the Hubble parameter. So this just says minus capital H. And that means the time derivative of momentum we can write as momentum times the Hubble parameter, nothing more. And that means the final equation that we're left with is this one. Okay. Now, I think I said in the previous lecture, and we'll return to this at the time when we're starting to do cosmological perturbation theory and structure formation. But what I think I said, I'll say it again, is that this microscopic Boltzmann equation contains all macroscopic fluid equations. So all normal macroscopic conservation equations are contained within this microscopic equation. And we'll see it explicitly for a few cases. But it's true in all cases. And it's, in fact, very useful to do momentum integration of this equation in various forms to derive what is corresponding to normal macroscopic equations. So let's try and do a few of those just to see how that actually goes. So we start from the fundamental conservation equation at the microscopic level. Then if we want a macroscopic equation, we should sum over all momentum states in a given spatial location, right? Because that would give us quantities like number density and energy density and pressure and so on. So remember, for example, that a number density we could derive by integrating the distribution function over momentum space in a particular location. And since all locations are equal in the cosmological principle approach, then this would apply at some specific time because the universe expands, right? So that's the number density. We could also do the energy density. Same thing, other than now we must weigh each state here with its energy, like this, and so on and so forth. So that means we can actually get conservation equations for this type of quantity by integrating that equation over momentum space. And the simplest possibility that we can do is to do the equation for number density, right? That's the very simplest possibility. So that would be this integral here of this equation. So then I would get an equation that looks like this. Now we can take these terms one at a time. So for example, we could start with the time derivative, but differentiation with respect to time certainly commutes with integration over momentum because these are unrelated variables. And that means that this first term here we can write very, very simply. If I multiply with this factor, then in fact what I have here is nothing more than the time derivative of the number density, right? Because I can move this outside the integral, and then I just have n as a result of my integration. So that particular part is very simple. Now the other one is slightly more complicated. So that's a term that looks like this. And then we should have a minus, and then p times h times the distribution function. Times, of course, this quantity here. Okay, so that looks like something we can do using integration by parts, and indeed that is true. So what we could do is we could rewrite this term into 4 pi p squared dp, because certainly we must have spherical symmetry, so the angular part of the momentum integral is trivial to carry out, just gives us 4 pi. Then I have p squared dp, so that altogether gives us something like, and then I have another p, so I get p cubed h df dp, like this. Okay, so most terms actually just go outside the integral, like the 4 pi and h. So I put these out here for now. And then I have, like this. Then I have this term here. And if I do that using integration by parts, then I should get p cubed times f at the boundaries, which would be 0 and infinity in this case, and then minus 3p squared f dp, like this. So the question is, what do I do with this term? Well, okay, it takes a little bit of thinking, but one can argue fairly easily that this term must be explicitly 0. And why is that the case? Well, if we look at the way we define macroscopic quantities, they're always related to integration over momentum space. So whatever I do up here, these integrals must always be convergent for any physically meaningful distribution function. If that's not the case, then I cannot do normal macroscopic physics, and of course that's in violation of fundamental principles. So certainly it must be true that this distribution function, if I multiply any power of momentum here or energy, that must go to 0 as p goes to infinity, because otherwise the integral doesn't converge. And that means f must go to 0 faster than any power of momentum I can think of. And that means it must go exponentially fast to 0. And indeed that's the case And that means that in the infinity limit, this must go to 0. The question is, what about the p going to 0 limit? Well, this I could write, for example, as p squared times f times 4 pi dp, this particular one here, right? So that certainly must be convergent also as I take p to 0. And that means that p squared times f must grow less fast than 1 divided by p, right? Otherwise, it wouldn't converge. And that means that, for example, this term must go to 0 because it's a higher power of p. It must go to 0 as p goes to 0. Otherwise, again, I get non-convergent integral. So no matter how I phrase this, such a boundary term must always vanish for any meaningful distribution function that you can have. And that means we're left with just this one term. Now what I do is I take the 4 pi back in. So I rewrite this. I take the two minus signs. They get to be a plus. So then I have a factor of h, 1 divided by 2 pi cubed. Then I have 3 times 4 pi p squared dp times f, like this. But when I do the integral, that's exactly number density. So what I get out in the end is actually 3 times the Hubble parameter times the number density, nothing more. And that means my conservation equation, the Boltzmann equation, when I integrate it over momentum space like this, can be cast as a conservation equation of this form here. And that's actually not super surprising, because we can look at what kind of solutions we would get to that equation. And then we get something not very surprising at all. Okay, so next part, if we look at that equation here, the n dot plus 3h n equal to 0, then we can rewrite this as a dot divided by a, and we can move that, and we get an equation that looks like this, which can certainly be integrated. And that will give us number density proportional to a to the minus 3. And then you might ask, is that a reasonable result? And the answer certainly is yes, because think of a co-moving box. You put particles in that box. The number of particles is a conserved quantity, but the volume goes as a cubed, right? So, and that means that the number density, which is the number of particles divided by the total volume, well, that must go as a to the minus 3 if you have conservation of total particle number. But that's exactly what you have, because the system is non-interacting, so you cannot take away particles or create particles. So this is the only result that would be meaningful in any way. Now, as a final test of what that Boltzmann equation means, let's also just do the energy conservation equation, just for some completeness, if you want. And then we will leave it for now. But remember, the energy conservation equation that we looked at, that was the one that looked in the like the following. So that was the one that we got from conservation of the stress energy tensor. You know, this covariant derivative of the stress energy tensor. The question is, can I also derive this from the Boltzmann equation? So then what I would do would be to do the same integration as before, but now wait with the energy per state, and then the Boltzmann equation in here. And then that should equate to 0. The first term, that's pretty trivial, right? Because again, remember, this commutes, and therefore what we get is the following. So let's just write it out. And then we get, oops, let's see. What I wanted was this. So let's try and see what that gives us. That gives us two terms. The first one is that one there, right? So that gives us this. And the second one would then give us